Hi, welcome to the Iowa State Geometric Analysis Seminar. Our speaker today is Xuan Hien Nguyen, who will be continuing with her series of talks. Today, she'll be discussing the vanishing of the fundamental gap of convex domains in hyperbolic n space.
Right. Thank you, Gabe, for the introduction. So I am doing this a little bit out of order chronologically. So we did prove this result first, and then I proved the one that was in the previous talk. This time it's going to be about convex domain. Let me remind you a little bit what the fundamental gap is and the results we had previous to this work. Again, given a bounded smooth domain omega, the eigenvalue equation of the Laplacian on omega is Laplace phi equals minus lambda phi. We're going to consider Dirichlet boundary condition, and you've seen in courses like applied math that the first eigenvalue is simple, and the second one is going to be strictly greater than the first one. There are many work on estimating eigenvalues of all kinds, especially the first one with all kinds of boundary conditions. The basic tool we use for these proofs is called the Rayleigh Quotient. So lambda 1 can also be characterized as the infimum of the integral of gradient phi square over integral phi square. And lambda 2 is the infimum over all the functions that are perpendicular to phi 1 of the same quotient. The fundamental gap is lambda 2 minus lambda 1, and it's going to be always strictly greater than 0. I'm recalling previous result for convex domain in Rn and Sn. So last time we did some example of one-dimensional segment and then two-dimensional very thin rectangle, and found that as the thickness of the rectangle goes to 0, the fundamental gap goes to 3 pi square over d square. So there was this conjecture that says, well, the fundamental gap of any bounded convex domain in omega, sometimes you can prove it with an extra potential here. So instead of solving minus Laplace equals lambda phi, you solve minus Laplace plus v, where v is a potential that's convex and non-negative. The fundamental gap is going to be greater or equal than 3 pi square over d square, where d is the diameter of your domain. We talked about why we need convexity to make the problem interesting. And these are just some important recent results. So Andrews Clutterbuck in 2011 proved the fundamental gap conjecture in Rn with potential. Hay and Wei proved it in Sn for n greater or equal than 3. And then Daisito and Wei proved it for n greater or equal than 2 in Sn. The question, I went to a Burr's workshop with Judy Clutterbuck and Guofang Wei, which is the Wei in here, and they were asking what happened in hyperbolic space. This is a result we have for convex domain on hyperbolic space. Last time I talked about hollow convex domain on hyperbolic space, and especially balls. So the first result was for hollow convex domain, and I showed that for n greater or equal than 2, there's a constant for which the fundamental gap is less or equal than the constant over d cube. This means that as d goes to infinity, it's lambda 2 minus lambda 1 times d squared goes to 0. Now this result says fundamental gap times d squared collapses, but d has to be big. And we've also had a previous article where we prove that the fundamental gap conjecture was violated, but also for big diameter d. And for a while, we thought, well, anything that happens in differential geometry when you are in a very small ball, then it's almost looking like you're on Rn. So we thought, hey, if we are in a very small patch, then surely the fundamental gap times d squared would be bounded from below. And this is why this result is surprising. It says that for any diameter, so once you have for any d positive, I can find a convex domain with diameter d. So think of these very small, such that the fundamental gap is less than epsilon pi squared over d squared. So lambda 2 minus lambda 1 times d squared also goes to 0 on very, very small domain. Not every small domain, but there are some small domain on hyperbolic space for which this happens. And this was surprising to us. It was also surprising to many people we sent it to. Today, I will talk about how to prove this result and what the domains look like. So here's the setting and the domains. We are going to work in the upper half plane model in H2. Everything can be, well, not everything, the result can be generalized to Hn with a lot of computation in coordinates, which I won't do here. So the domain looks like this, and it's not quite polar coordinate because phi equals 0 is actually the y-axis. The only reason is because we have symmetries around phi equals 0. So phi here goes from minus pi over 2 to pi over 2 for the half plane. The metric is this metric where you divide by y squared. That means that as you get close to the x-axis, distance just grow. This is the polar coordinate equivalent. And the domain, for the domain L is going to be fixed. And it's the angle here. So it goes from, phi goes from minus L to L. And R goes from 1. So this is R equals 1. And this is R equals some exponential. The exponential, you will see in a second, is nice because we'll get an ODE with a change of variable. And it's a good change of variable for the ODE. And this is the domain. Now, the next slide, we're going to compute the diameter of the domain, or estimate it. We call the metric. So I was doing computation where, given 2 points, you can find the geodesic, and then write this curve, integrate with this weight, ds, and find the distance between 2 points, which is when one of my co-authors was like, hey, have you looked at Wikipedia? And Wikipedia tells you the distance between the point of Cartesian coordinate x1, y1, and x2, y2 is r cosh of 1 plus x2 minus x1 square plus y2 minus y1 square, and the last part over 2y1, y2. The computations were beautiful. Everything was simplifying, but this is a nicer, faster way. Okay. Note one thing. This is scale invariant. By that, I mean that if you look at the distance from A, x1, a, y1, to a, x2, a, y2, so multiply both by a, is exactly the distance from x1, y1 to x2, y2. With this remark, you can see that the distance from P to S is equal to the distance from Q to R. And in fact, any distance along half circles on the same from here to here. So any distance from a point here to there is going to be the same. What is the diameter? The diameter of this domain can be proven to be the distance from P to R. Okay, so kind of the diagonal, or S to Q, which is the same thing. There's a little bit of a geometric argument here that if you have 2 points that realize the diameter, they can't be inside because the geodesic connecting them has to be perpendicular to the boundary. And so they can't be inside any of the segments, so they have to be the points at the corners. And comparing the distance from the point, one point at the corner to another point at the corner, you find that the biggest distance is from P to R. It makes sense. You can think of this maybe as a rectangle. So what is the diameter? Well, distance from the diameter then is the distance from P to R. Then it's greater or equal than the distance from P to S, which is less or equal than this thing that I'm going to draw. The distance from P to T, T to U, and then U to R. If you compute the distance from P to S, let's write it here. P is, so x1, x2, x1, x2. So it's sine L cosine L. And S is minus sine L cosine L. Okay. Put it in the formula above here. And we get that this is arc cosh of 1 plus 4 sine square over cosine square, 2 cosine square. That's D. And here, as I showed, distance from R to U is the same as distance from S to T. So it is also arc cosh, 4 sine square L over 2 cosine square L, plus the distance from U to T, which is written on the next slide. So remember, we established this guy, and this is the distance from U to T. This is, well, not important. It is very convenient because notice what, so I forgot to tell you, what we will do with our domain is we will let mu goes to infinity. So the domain was like this. The radius inside was 1. The radius outside was e to the pi over square root mu. We're going to let mu go to infinity. When mu goes to infinity, we still have a bound, a lower bound and an upper bound on the diameter. So the point was to estimate lambda 2 minus lambda 1 times d squared. So I don't really have to care about d squared. It's not going to infinity. It's not going to 0. So we're just going to look at lambda 2 minus lambda 1. And if we can prove that this goes to 0, then lambda 2 minus lambda 1 d squared goes to 0. Okay, now let's set up the problem. Remember, the equation was Laplace u equals minus lambda u. We're gonna separate variable. Remember also that ds squared was dx squared plus dy squared over y squared. And in 2 dimension, when you multiply the metric by this thing, the Laplace gets multiplied by the inverse. So the metric gets multiplied by 1 over y squared. The Laplacian in that metric is y squared and Laplace of u in R2. Now let's switch to polar coordinates. Y is r squared cosine square phi. I know cosine square is strange, but that's how we choose our variable. And this is the Laplace in metric, in R2. Phi, u phi phi. And that equals, let me make some room here. Equals minus lambda u. Separate variable. So u equals h phi fr, and divide both sides. Let's separate variable and divide at the same times. R squared cosine square phi frr over f plus r squared cosine square phi fr over f. There's no square because the square gets, so there's no square, plus h phi phi divided by h, and the r square cosine square cancel, minus equals minus lambda. So we regroup this together and this together. The left-hand side is a function of r if I divide by cosine square. So let's divide by cosine square. This is a function of r only, so it has to be equal to a constant. K square mu. This is just a convenient way to write the constant. You see that this is like an exponential change of variable would make this just as FRR, a second derivative, which is why we had exponential for the radius. And mu here is because of the boundary condition f equals 0 on the smaller radius and the larger radius. The second one is this, and while I'm multiplying by secant square phi k square mu. So there's something in the computation. I don't know why I have an extra cosine square here. This is the separation of variable. And you have these two equations. it kind of mirrors what we had with rectangles when the height was this guy, and then there was an ODE for this dimension. So now the question was, well, k equals 1 gives you the smallest guy here, but then we can take the first eigenvalue for k equals 1, which is this guy, or we can take for the second eigenvalue is either the second eigenvalue, second lambda for k equals 1, or the first lambda, first eigenvalue when k equals 2. Well, we don't really need to know which one is smaller, because whichever one is smaller, it's going to be less or equal than lambda 2 when k equals 1. So the fundamental gap is always going to be less or equal than the difference of the second eigenvalue of this equation minus the first eigenvalue of this equation. So the whole problem, if you have a domain that allows separation variable and you do the computation correctly, this is reduced to finding solutions or estimating eigenvalues of this ODE. So the rest of the talk will be focused on just this ODE. Now, before I get into the proof, I will talk about why this works. And it's kind of funny because after we did the proof, we discussed what it was. And this picture actually explains a lot. And once people see this picture, even though it was a surprising result, they're like, okay, this is what's happening. I understand it. This is not such a great result, which is pretty sad. So in the half-plane model, the domain looks like this. But if you draw it in the Poincaré model, it looks like this. So what the Poincaré model shows you is that this distance in the middle is actually smaller than this. So UT is smaller than, say, PQ. Therefore, we have a neck here. And last time, I explained why when you have two things connected by a very small neck, the fundamental gap, the difference of the eigenvalues will go to 0. And this is exactly what's happening in our domain. So it doesn't matter what L is. L could be like this, and you can have a domain with a small diameter. This distance is still smaller than this distance, and you still have a neck. And as mu goes to infinity, that means as the domain gets thinner and thinner, the neck gets thinner, and the fundamental gap goes to 0. So the proof, the plan is to show that the first eigenfunction behaves like this thing, where kind of at the neck, it goes to 0, and it looks almost like, well, it looks like two different domains connected by a neck. Show that the maxima here will move towards minus L and L as mu goes to infinity, and that H1 of 0 would go down towards 0 and make everything precise. And so once we have that, the second eigenvalue, lambda 2, would be estimated by using the Rayleigh quotient with a test function that is perpendicular to H1. And to construct a function that's perpendicular, we just go like this, and then on this side, instead of going up, we just flip it. A way of flipping it is just multiplying it by this transition function, this piecewise Lipschitz, piecewise defined Lipschitz transition function. And phi1 would be of order 1 over mu. Okay. So as mu goes to infinity, we will show that this goes down to 0, and the transition here doesn't contribute that much. So then lambda 2 minus lambda 1, Rayleigh quotient, the difference would only happen here, and we show that that goes to 0. So first, we have to have a hold on the first eigenfunction. The main ingredient is something seen in the ODE, is that if you have two positive functions satisfying f1 second plus b1 f1 equals 0 and f2 second plus b2 f2 equals 0, if they're both 0 at 0, but b1 is greater than b2, that means that this is quote unquote more concave down, so it goes down faster, then x1 has to be less than x2. So if this was your 0, if this was your f2, and it 0 and x2 are consecutive roots, f1, if b1 is greater, it kind of dips down faster, so x1 has to be less than x2. And that's, well, that's the main ingredient for the beginning of the proof. So first, we thought this is our equation, ODE. We're just going to talk about ODE. A bound from below, that lambda 1, as mu goes to infinity, the first eigenvalue, lambda 1 times secant L square, is greater than mu. And I get confused, so I have to write exactly the same thing with cosine. The proof is very simple. Suppose not. Then lambda 1 secant L square minus mu is less or equal than 0. That means that lambda 1 secant phi square minus mu is less or equal than lambda 1 secant L square minus mu is less or equal than 0, which means that if you rewrite this as h phi equals minus lambda secant phi square minus mu h, this is less or equal than 0. This is greater or equal than 0. So this is always greater or equal than 0, which contradicts the boundary condition. H has to be 0 from at minus L and L. Dirichlet boundary condition. So it can happen. The second estimate is a bound from above. Now it says for every eta between 0 and L, there exists a mu2 such that mu is greater than mu2 implies that lambda 1 secant eta square is less or equal than mu. So remember the previous one said lambda 1 secant L square is greater than mu. But here I'm saying for anything that is so yes, for anything that's strictly greater, so lambda 1 secant square is greater than or equal than mu. Think of it as, let's see, think of it as this guy. Okay, lambda 1 over mu greater or equal than cosine square. I'm saying for anything that is strictly greater if eta is between 0 and L, cosine eta would be greater than cosine L. For anything that's strictly greater than cosine L, I can find a mu for which lambda 1 over mu is less than that thing. So the upper bound and the lower bound here implies that lambda 1 over mu would go down to cosine L squared. So I have convergence. This is really what the bound from above tells you. Anytime you have anything that is greater than this guy, okay, this is greater than that, then I can get my quotient to be less or equal than that for mu large enough. Okay. So let's do the proof. The proof is, again, using the comparison principle. Okay. So suppose there is something and a sequence mu k going to infinity so that this is violated, so this is greater than mu k. Then lambda 1 secant phi square minus mu is greater than lambda 1 secant phi square minus secant eta square. Just replace this in here, and then you get that. Which means that this is for all eta, the right-hand side goes to infinity as mu k goes to infinity. So this is positive. What about lambda 1? Well, from here, you go that if mu goes to infinity, u lambda 1 goes to infinity. So this whole thing goes to infinity, which says that you have an h. This is, think about it's infinite. You have an h that starts at minus L. 0, it goes up. But h phi is so, well, goes to minus infinity. So it's going to go down really fast. And that will contradict the fact that you have Dirichlet boundary condition and that the first time it hits 0 after this has to be at L and not right here. So this really can't go to infinity if you hope to go from minus L to L, staying positive. That's the proof by contradiction. So why was it helpful? For me, the key fact was proving this, okay? If you look back at the equation here, you get two inflection points. Basically, inflection point is where the second derivative is 0, so h is never 0. You get inflection point where this equals 0. And that equals 0 at some phi star, and the phi star, secant of phi star square is mu over lambda 1. Just solving that. That means that cosine phi star square is lambda over 1 over mu. But we just proved that this goes down to cosine L square. So phi star goes to L. Phi star are the inflection point. I have a graph of the first eigenfunction. It's symmetric with respect to this line because the equation is symmetric. And I have two inflection points here and here, which is phi star and minus phi star. So it's going to look, and if you look at the sign of the second derivative is positive here, then it's negative here, then it's negative here. And we just showed that these inflection points go to L, which also shows that the maxima here go to L. Okay, so it's going to start doing that. Then there are two things that happen now. There is a integral estimate, which I'm not going to show you the proof. But essentially, once you know that your profile here, that this moves out, we just pick a really random phi naught and minus phi naught and fix it. And what will happen between phi naught and minus phi naught as things move out, this will go down. And it will go down, and we can quantify it by an integral estimate, that the integral in this region in the middle is less than a function, and that function goes to 0. So the integral in the middle is going to go to 0 of h1 square secant phi square. And this is a pointwise estimate. It's another comparison theorem. Because the first eigenfunction is symmetric, the first derivative at 0 is 0. And so we can compare it to other solution of second order ODEs for which the coefficient in the middle is positive. So it happens to be cosh, because it's a combination of exponential, and cosh has h prime at 0 equals 0. So inside here, h is less than or equal than its initial value times a cosh, and it's actually squeezed into two cosh function, depending on your upper bound and lower bound of the Laplace, the lambda secant square minus mu. So we can combine these two. Say it has to be cosh, and cosh grows super fast. But the integral in the middle goes to 0. So the only way that this happens is if this guy goes to 0. Okay. We can quantify that, and we have a bound that says h1 0 square is less than some exponential with negative argument. Then using this, we run through the estimates again, and we can actually estimate now, have better estimate. Phi 1, what was phi 1? Phi 1 was, so phi naught, this is minus L, this is L, this is phi naught and minus phi naught. We knew that it was doing this, and then it was going towards it, getting smaller and smaller, and here. And phi naught was our transition region. Phi 1 is phi naught over mu. So it's where we go from positive to negative, from h1 to minus h1, and we transition in a very, very small region. But we also have very good estimates here. So here's the last part of the proof. Write the Rayleigh quotient. Remember, Rayleigh quotient was R of h was minus L to L of h phi square plus mu h square d phi over integral from minus L to L of h square secant phi square d phi. And what was psi? Psi was just the function that goes from 1 to -1, and it made the transition between minus phi 1 to phi 1. So something of order 1 over mu. So the slope here is of order mu, which blows up. Now you do the usual trick by, kind of how you add and subtract this number to split it into different portions. So A, well, h1 square minus psi h1 square, it's fairly benign, nothing bad goes here. We needed a better estimate for this guy, for B, because, well, if you take the derivative of psi, it's of order mu, and you square it, it's of order mu square. But we have this estimate that says, look, if I integrate h1 square times mu square and let mu go to infinity, they go to 0. So this goes to 0, this goes to 0. And we show that each part of these goes to 0, therefore the difference of the Rayleigh quotient goes to 0. And this is the last slide. I show that the difference of the two eigenvalue for the ODE goes to 0 as mu goes to 0. Therefore, the fundamental gap of my domain goes to 0 as mu goes to 0. Again, because, well, this is the fundamental gap. And it's possible to generalize this to higher dimension. It's actually, we use the result in H2, and we kind of reduce dimension by doing some induction. You can see that in higher dimension, you have the same principle with this picture. If you have two hyperplane, then there's still going to be a neck between them. And that's the end of the talk. Thank you for your attention.
Thank you.
And,
So any questions?